Sequences and series. To begin with, of course, we will see the definitions and examples and some terms associated. But I want to tell you, well, firstly, the difference. Okay, sequence is not a series. Okay, sequence and series are two different entities, or I would say are two different mathematical objects. Secondly, well, this may not be relevant to maths, but series is used as both a singular and as a plural. Okay, whereas for a sequence we say sequences if we have two or more sequences, but for a series we just say a series, okay, or many series. Correct? Okay, so let us now start the revision. Alright, first let us define a sequence. First, let us define a sequence. So what is a sequence? Sequence is defined as a function whose domain is the set of natural numbers. Okay, sequence is a function whose domain is the set of natural numbers. But okay, so for us this definition is fine. Okay, we are fine with this definition. But usually, like especially in computer science, when they use sequences, they also they may modify the domain, or rather extend the domain to integers, or more generally the set of integers. Okay, and let us now consider the notation. The notation is usually f of n or Tn. So that basically tells us how to find the terms with input n. Okay, number 2. What is a series? Now this is where the difference between a sequence and a series will become clear. A series is sum of finitely or infinitely many terms of a sequence. So now you understand that in a series we basically take two or more terms of a sequence. There may be infinitely many terms also. We'll see that later, or finitely many, and just add them up. So essentially series involves summation or addition. Essentially a series involves addition or summation, whereas a sequence is just a function. Okay. Now a closely associated term with a sequence is a progression. Okay, so do you people remember the difference between sequence and progression, or shall I tell that? Yes, do you people remember it?
Yes, sir. I mean, I don't really know the definition per se, but yeah.
Okay, tell us the difference then. Very good. Oh, no, I'm not talking about that. See, look. Okay, I got it. Look. See, sequence is essentially a function, right? And because it is a function, there isn't any, I would say, order associated with a sequence, right? So let's say, for example, when I say f of n is equal to, let us say, n squared. When I say f of 3, you will say 9. When I say f of 5, you will say 25. But in a progression, we kind of arrange the terms in a sequence in a specific order. Okay, and then it becomes a progression. Terms in a sequence are arranged in a specific order. and therefore it is called progression. So the f of n notation is common for sequences, but because we consider them as progressions, we use the Tn notation. So when I say T subscript n, or in some books they also use A subscript n, when I say this as n squared, then the whole sequence gets specified, and the corresponding progression also gets specified, right? So when it is 1, 2, 3, 4 and so on, Tn will be 1, 4, 9, 16 and so on. Okay, so the only minor difference between a progression and a sequence is that in a sequence there is no compulsion to write the terms in a specific order. Whereas in progression there is this compulsion. We always write that term first which we get on substituting n equal to 1 in the definition of the progression. Is it clear? That's the difference. That's fine, but we will consider sequence and the progression as synonyms. Okay. All right. Let us now start discussing some commonly studied sequences or progressions. The first one among them is called arithmetic progression or AP. Okay, so how is an AP characterized? An AP is characterized by two parameters, and these two parameters are called the first term, often denoted by A, and the other parameter is denoted by D, which is called the common difference. And what is the characteristic of an AP? Difference between two consecutive terms is constant. Okay, difference between two consecutive terms is constant, right? It's constant. So if I go to T2, I know that T2 minus T1 is D. Okay, that difference is called common difference, as the name suggests. When I say T2 minus T1 equal to D, T2 becomes T1 plus D. When I say T3 minus T2 is equal to D, T3 becomes T2 plus D, but T2 is already T1 plus D, so it is T1 plus 2D. Right? So in general, if I go for the nth term, it becomes the first term plus n minus 1 times D. Okay, and that pattern is not very difficult to spot. Because we are going to the third term, it should be 2 times the difference away from the first term. Okay, so if we are at the nth term, it should be n minus 1 times D away from the first term, and hence the general formula. So this is the main formula associated with an arithmetic progression, and that formula is for the nth term of the arithmetic progression. Tn is equal to T1 plus n minus 1 into D, or A plus n minus 1 times D. Okay, that is the formula for first nth term of an AP. And similarly, we can also get a formula for sum of first n terms. Okay, we can also get a formula for Sn, which essentially means sum of first n terms of an AP. Okay, so does anyone know the formula? Look, I'll tell you how to derive the formula quickly. Every term is going to have the first term, so it is going to be n times A plus, now look, there is this D here, okay, there is this D, but this D is to be added how many times? 1D for T2, 2D for the second term, third term, 3D for the fourth term and so on. But how long are we supposed to go? Till n minus 1. And you may already be knowing this formula. For sum of first n natural numbers, it is n into n plus 1 upon 2. So in this case, it is sum of first n minus 1 natural numbers. So it is n minus 1 into n, or n into n minus 1 upon 2 times t. We will see this formula later, that sum of first n natural numbers is n into n plus 1 upon 2, but we have applied it here. Okay, so don't learn it by heart. I think you can derive this formula quickly even if you forget it in the paper. Right? Is that clear? Sum of first n terms? Yes? Okay. That is for AP. Now usually we can solve the problems on AP if we know the nth term formula and sum of first n terms formula. But there are some things that it's better if you know them. So we will now go through them. Okay, useful results on arithmetic progression. First, if a constant is added to or subtracted from each term of an AP, then the resulting sequence is also an AP with the same common difference. Okay, let's verify this. Suppose I take an AP with first term 2 and suppose common difference 3. So what will be my terms? 2, 5, then 8, then 11, 14 and so on. Okay. Suppose I choose to add 2 to every term. So I'll get 4, 7, 10, 13, 16 and so on. Right? That is also an AP. First term has changed. First term here is the original first term plus the number that we chose. But did the common difference change? No, it did not. Okay, the common difference remained the same, and it is going to remain the same no matter what number you choose. You can either choose a positive number or a negative number, right? Okay, so that is the first result. You may already know it. Next result is multiplication. What happens if you multiply every term by some number? If each term of a given AP is multiplied or divided by a non-zero constant k, then the resulting sequence is also an AP with common difference kd or d upon k respectively, where d is the common difference of the given AP. Okay, I think this is also simple. Let's again stick to our AP as a equal to 2 and d equal to 3. 2, 5, 8, 11, 14, 17. Okay. Suppose we decide to multiply this by half. That is as good as dividing it by 2. Correct. So it will become 1. 5 by 2, 4, 11 by 2, 7, 17 by 2 and so on. So this is also an AP. This is also an AP. What is the first term now? The first term here is clearly the original first term times the number that you chose to multiply the whole AP by. Okay? Now it is the common difference. You see what is the common difference here? 5 by 2 minus 1, that is 3 by 2. Right? 4 minus 5 by 2 is also 3 by 2. But what is this 3 by 2? Here, the 3 is already there and it has got multiplied by 1 upon 2. Okay, it has got multiplied by 1 upon 2. Okay? It's another thing that you should know about AP. Yes. Now this, we can again pick our previous example for this. If terms of an AP are chosen at regular intervals, then they also form an AP. To put that point, let us consider the same AP here. Okay, let us consider the same AP. When I say if we choose terms at regular intervals, it means the gap should be same. So suppose I pick every alternate term, 1, 4, 7. Okay, what will come next? Next we will have here, it was 3 by 2 there, right? It was 3 by 2, so 10. So that will also be another AP. Okay, that will also be another AP. Of course, its common difference will be different. It depends on the span, the gap between the two terms, and also it depends on what first term you chose. But the point is, if we choose them at regular intervals, equally spaced, so I can also pick 1, 11 by 2, and then the next term will directly be equal to 10. I can also pick 1 and then 7. I can also pick 1 and then 10. Okay, are you getting this?
Yes, sir.
Okay. Yeah. Now these are also some standard situations. Suppose three terms of an AP are to be found out. Okay, three terms are to be found out. It's better to choose them as A minus D, A plus D, rather than A plus D, A plus 2D. See, this is perfect. This is a correct choice. We can still do A plus D and A plus 2D. But the benefit of choosing the three terms as A minus D, A plus D is that, okay, the benefit is that the addition does not involve D. So if we know the terms, if we know the three terms, rather their addition, okay, if we know their addition, then it's just 3A. Okay, addition is 3A. One of the situations in geometry where they make use of this fact is, there could be a question like, if angles of a triangle are in AP, then, and there will be something else. Okay, but here you can prove that if we take the angles as A minus D, A and A plus D, it becomes 3A because D gets cancelled, so it becomes 180. We know that, right? So what will be A? 60 degrees. Which means if angles of a triangle are in arithmetic progression, then the intermediate angle has to be 60 degrees. The other two angles can then be chosen depending on what the common difference you take. If you take it as 10, then it will be 50, 60, 70. If you take the common difference as 20, then it will be 40, 60, 80 and so on. Okay, so A minus D, A plus D is a better choice than A plus D, A plus 2D, especially when sum is given, addition is given. Similarly, if we have 5 terms, then don't choose them as A plus D, A plus 2D, A plus 3D, A plus 2D, that's correct. But from the solutions point of view, it's better if we choose them as A minus 2D, A minus D, A plus D, A plus 2D. Okay. Now if we want to select two terms of an AP, see here, look, what we usually do is, we usually pick them as A minus D and A plus D. Now from this property that we just now discussed, if the terms of an AP are chosen at regular intervals, the result will still be an AP. Same thing. Ideally it is A minus D, A plus D. Okay, but here why did I choose it as A minus D or A plus D, or rather why is it better? Again, the benefit is that sum or addition is 0. Okay, addition is 0. What is the addition? Addition is 0. Sorry, addition is not 0, sorry. The D part goes, addition is 2A. The care that you should take in making this particular choice is that the common difference that you want is actually 2D, A minus D and A plus D. Right? If we consider them as two consecutive terms, what should be the common difference? Usually it is D, but in this case the common difference is 2D. Are you getting my point? A plus D minus A minus D, that's 2D. Okay? Thank you. Next, if we select 4 terms, same logic. Take the common difference as 2D instead of taking it as D. So A minus 3D, A minus D, A plus D, A plus 3D. So when we have an odd number of terms, there is no issue as far as D is concerned. But when we have an even number of terms, then that issue pops up because there is no middle term. Something similar we have experienced when we were discussing median of a data set in statistics, right? If the number of terms is odd, we can easily locate the median. If the number of terms is even, then we have to pick the two central terms and then find its arithmetic mean. That is chosen as or taken as median. Okay, so same thing. Acha. Now I want to tell you one more thing about AP, which is I think you do not know. If you know it, better. If you know, nothing like it. Okay. So this is the thing. If we plot n comma tn of an AP, on a graph paper. Okay, what curve will we get? Okay, will it be a curve or a line? It will be a straight line. We get a straight line. What is the slope of the straight line? Can anybody tell me the slope? Acha, okay, first of all let us argue why is it a straight line. Okay, why is it a straight line? Look, the property of straight line is that y2 minus y1 upon x2 minus x1 is same constant, and that constant is called as slope. Right, and here we have that tn minus 1 upon n minus 1, that is actually d. Right, that is actually d. Is it clear? Did you understand this part?
Yes, sir.
This part is important. This part is important. Okay, fine. So what is the slope of the line? Slope is actually common difference, and you can then pick any point that you want as the starting point. Okay, slope is always common difference. Let's consider it. Okay, so let's go back to the sequence that we had considered. Suppose the first term is 2. Okay, suppose the first term is 2, and suppose the common difference is 3. Okay, common difference. See, what line does it represent, or on what line do all points on this particular arithmetic progression lie? If somebody asks you that question, what you should do is you should first write down this: Tn is equal to a plus n minus 1 times t. Right, Tn is equal to a plus n minus 1 times t. Replace Tn by y. First term is 2. N minus 1 is okay, so that's there. And t will be sorry, n should be taken as x. Sorry, n should be taken as x. N should be chosen as x minus 1 times 3. Okay, so what is that? 2 plus 3x minus 3, or 3x minus 1. Okay, so that is the line. Now let us see if that is right. Okay, so first term is 2. Second term is 2 plus 3, 5. Third term is 5 plus 3, 8. Fourth term is 11, and so on. Right? Okay, let's see the line 3x minus 1. See, that line passes through all the 4 points. Okay, so graph of an AP will always give us collinear points. Okay, rather I should have said collinear points I should have said, but if we join them, then we get a straight line, because AP is essentially a discrete structure. Right? It's not a continuous structure like a line. But well, the thing that I want, the thing that I meant to be said here is, if we join those points, then we'll get a straight line. Okay, I hope you followed that.
Yes, sir.
Yes, sir.
Okay, thank you. Cool. So the slope is essentially the common difference, and then you can very easily put x is equal to 1 to get the first term. Okay. Great. So that's it about AP. Now let us go to geometry progression. Okay. Give me a second. Okay. Now in GP also 2 parameters are required. 2 independent parameters completely describe the geometric progression. Among them, first parameter is the first term, and the second parameter is called R, which is the common ratio. Okay, this is called as common ratio. And in AP, what is constant? In AP, the difference between 2 consecutive terms is constant, Whereas in GP it is the ratio that is constant. Okay, in GP the ratio of two consecutive terms is constant. And that's why that ratio is called as common ratio. So T2 by T1 is R. So T2 becomes T1 times R. T3 by T2 times R. So T3 becomes R times T2. But T2 itself is T1 into R. So it will be T1 into R squared. In general, nth term is equal to, okay, nth term is equal to first term into R raised to n minus 1. Or I can say Tn is equal to A into R raised to n minus 1. Okay, that is the formula. First essential formula for GP. You should know the formula. Okay. And the second formula is called is for sum of first n terms of a geometric progression. Sn is sum of first n terms of a geometric progression. Now this formula can be proved, but I'm not going to prove that. I'm going to write the formula. It is A into 1 minus R raised to n upon 1 minus R, assuming R not equal to 1. Of course, there is no point in R equal to 1, otherwise it will become a constant sequence. Okay? Do you people know this formula?
Sir.
Yes, you know
Yes,
it, right? Okay, very good. Alright. Now let us see some terms, useful information about GP. Like what happens if we multiply or divide. That's it. Yeah. Acha. Firstly, well, we know this. This is just an extension of what we discussed in AP. Okay, if we have three terms and if the product is known, it is better to assume the terms to be A by R, A, AR. Again, the benefit is clear. Benefit is that product is independent of R. Right? The product is independent of R in either of the cases. For an odd number of consecutive terms, it's easy. The central term is to be considered as A and everything else gets adjusted or is to be adjusted accordingly. But if we have an even number of terms, then the common ratio that we should consider is R squared. Okay? Same thing. There we consider the common ratio as 2D. Here we are considering it as R squared. Okay? Fine. Yeah. If all the terms of a GP are multiplied or divided by the same non-zero constant, then it remains a GP with the same common ratio. Okay. So let's take A as 2 and let us take R as, okay, let's take it as 1 upon 3 this time. Okay, so what will be the GP now? 2, 2 by 3, 2 by 9, 2 by 27 and so on. Suppose we multiply this by some non-zero constant. Okay, suppose I take it as 3 by 2. Okay, suppose I take it as 3 by 2. Then what is the new sequence that I'm going to get? 3. 3 and then 1. And then 3 by 9, that is 1 upon 3. Then I'm going to get 1 upon 2. Then I'm going to get 3 by 4 and so on. Right? And is this the GP? Is this the GP with same common ratio as the previous one? Yes. 1 by 3 here, 1 by 3 here. Oh no, something is wrong here. Wait. Where did I go wrong? Into 3. 2.
Sir,
Yeah,
it's
in this.
1 by
Yeah.
9.
No. Here. Sorry, my mistake. I think the second term itself is something which... Oh, wait. Let me figure it out. Okay, we have...
Sir, the fourth term, it should be 1 by 9, not 1 by 2.
Okay, wait. Into 3 by 2, so this is correct. This is 1. Into 3, no, third term is wrong. This should be 3 by 2. Again, by mistake, I multiplied by 1 upon 3. Okay, third term is wrong, sorry. My third term is wrong. It's not 3 by 9, it's 3 by 2. third term is 3 by 2. Then fourth term should be 9 by 4. Okay, 9 by 4 and then 27 by 8. So yes, I think now it is right. 1 upon 3. Wait a minute.
No, sir.
Okay. Okay, first term is correct? Correct. First term is correct. Second term is correct?
Yes.
Oh, okay, no, second term is wrong. Second term is 3 by 2. My mistake. Okay, who said that was wrong? You, I think. Danish?
No, sir. 2 by 3 into 3 by 2 is 1, right?
Wait. Oh, okay, my bad. Okay, let me keep my mistakes there and I'll do it again. Okay, let's do it here. I think what I did was later on I went on multiplying this by this sequence itself by 3 by 2. Okay, that was not the common ratio, that was the number. Okay, so that's 3, that's right. 2 by 3 into 3 by 2, that is right. Then it will become 3 by 9 or 1 by 3. Then it becomes 3 by 27. Okay, correct. Sorry, I was considering it as a common ratio rather than the number. Okay, it remains the GP with the same common ratio? Yes, the common ratio is 1 upon 3. Okay, fine. That property is clear. If each term of a GP is raised to the same power, then the resulting sequence also forms a GP. Okay. So suppose I take A as 2 again, and suppose I take R as 1 upon 3 again. Okay. So what will be the GP now? 2 by 3, 2 by 9, then 2 by 27 and so on. Suppose we raise it to 2. Okay, suppose we raise it to 2. 2 squared 4, 2 by 3 squared 4 by 9, 2 by 9 squared 4 by 81, 2 by 25 squared 4 by 729 and so on. Okay, now what has happened to the common ratio? What has happened to the common ratio? The common ratio has become 1 upon 9, which is square of the original common ratio. Right? It is the square of the original common ratio. Okay, so this also forms a GP with common ratio some power. Which power? The power to which it was raised. Okay? Okay. You also know this. 3 non-zero numbers ABC are in GP if and only if B squared is equal to AC. Okay, now when is that true? Or rather, how is that true? When I say B squared is equal to AC, I mean B by A is equal to C by B. That means if ABC were 3 consecutive terms, okay, 3 consecutive terms of a GP, then we would have got the same result, B upon A equal to C upon B, and hence that biconditional statement is proved. B squared is equal to AC means A, B, C are in geometric progression. Okay? Fine. Okay, now I want to discuss few more terms about GP. Among them, first is sum to infinity. Okay, among them the first one is sum to infinity. Point 1. S infinity. Now S infinity is defined only or if and only if the common ratio's absolute value is less than 1. Okay, the common ratio's absolute value is less than 1. Otherwise S infinity is not defined. Okay, S infinity literally means what happens if we continue to add all the terms of a sequence? Now, if you go back to the formula that we had written earlier for Sn, okay, which is a into 1 minus r raised to n upon 1 minus r, that formula. In this formula, this term becomes so small for larger and larger values of n, because common ratio is absolute value less than 1, that in the limiting case we can ignore it. Okay, we can ignore it because its contributions become smaller, smaller and smaller. So this is equal to a into 1 upon 1 minus r. Is it clear now?
Yes, sir.
Yes. Now this result has a special significance. This result has a special significance which you may not be knowing, or rather you should, you may be knowing it. Okay, and that is, look, S infinity is essentially this, right? And that is a into 1 upon 1 minus r. And if we cancel a, what are we getting? We are getting 1 plus r squared plus r cubed and so on. And that is actually 1 upon 1 minus r, or 1 minus r raised to negative 1. 1 minus r raised to what? Negative 1. Now we can also get this using binomial theorem. We have done that. Also obtained by binomial theorem. That's the first significance. And the second significance of this result is that in higher mathematics, we study something which we call power representations of functions. So if we take a function f of x, okay, if we take a function f of x as 1 upon 1 minus x, of course with its domain to be open interval -1 to +1, then its power series representation is 1 plus x squared and so on. Right? You will study this later also, and I will tell you some examples of power representations, but you now have got a hint that just knowing the power series representation of a function is not sufficient. Additionally, we should know for what values of x does the power series representation looks meaningful, right? Because if we take, let us say, the number as 2, left side is going to give us -1, but what about right side? It's going to give us a number, an ever increasing number. Now that doesn't make sense. So this part is important. Okay, domain. And how has that come? Rather, why has that come? That has come because of this formula for SF, for GP. Okay, that Rn terms, Rs to n terms contribution to the sum continues to vanish. So we say in the limiting case it becomes 0. Okay, that's the first thing. Second thing is that if we plot the terms of a GP, if terms of a GP are plotted, okay, that is n comma tn. Okay, which curve will we get? Any idea? Will we get an exponential curve? Yes. Look, how will we get it? Okay, how will we get it? Let's again take our example. A equal to 2, R equal to 1 upon 3. What is Tn? A into R raised to n minus 1. So what will it be? 2 into 1 upon 3 raised to n minus 1. So I can modify this as okay, how can I do that? 2 into 3 raised to negative n plus 1, right? So I can say 6 into 3 raised to negative. If I take the function y as 6 into 3 raised to negative x, if I take this as my function, then all the terms of our GP, they will lie on that particular exponential curve. Okay, they will lie on that particular exponential curve, 6 into 3 raised to negative x. Okay, now let us see if that is indeed true. Okay, let us see if that is indeed true. Our first term is 2, our second term is 2 by 3, our third term is 2 by 3 into 2 by 9, our fourth term is 2 by 27, and so on. Let's plot one more. Fifth term is 2 by 81, and if I go to the curve y equal to 6 into 3 raised to negative x, all of them are found to lie on that curve. See that? So all the points of, well, all the terms of a GP, if considered as points on xy plane, if we draw a smooth curve passing through all of them, then we will get an exponential curve. Is that clear?
Yes, sir.
Okay. Now it would be interesting to see what happens if the common ratio is negative, because if we take the common ratio to be negative, okay, then the signs of the terms are going to flip. Okay, the signs of the terms are going to flip. So let's take that example and see what happens. Okay, let us see that example and see what happens. So I'm going to keep a as it is, but I'm going to change my common ratio to negative 1 upon 3. I'm going to change it to negative 1 upon 3, and now I want to see what happens. So Tn is 2 times negative 1 upon 3 raised to n minus 1. Okay, negative 1 upon 3 raised to n minus 1, so 2 as it is. Okay, so let us take this as negative 3. Let us take this as negative 3. Which one? The negative 1 upon 3 raised to minus 1 part into negative 1 upon 3 raised to n. Okay, so this is going to be negative 6 into negative 1 upon 3 raised to n. So which function shall we plot? Y equal to negative 6 into negative 1 upon 3 raised to x. Okay, fine. Let's see. So first term is 2. This will be negative, this will be positive, this will be negative, this will be positive. Let's take one more. 6 comma 2 by 243, and this term should be negative. Okay, this term should be negative. Negative 6 into negative 1 upon 3 raised to, wait, what's that? 1 upon 3 raised to x. Oh, okay. No, that has given us some imaginary values, and that's the reason why we have not got it right. Okay, maybe we should take mod here. Is mod defined? No, see, the mod is not defined. Why? See, for example, see, it's a continuous curve, right? It's a continuous curve. We expect that. So if I take x as 1 upon 2, if I take x as 1 upon 2, then we will enter the region of complex numbers, because the root of negative 1 and therefore root of negative 1 upon 3 is going to be purely imaginary. And that is why this particular thing that I have said here, n comma t, and we will get an exponential curve. This is valid only when r is positive. Okay, this is valid only when r is positive. Are you getting that?
Yes, sir.
Okay. Otherwise we cannot plot them on a single curve. We cannot plot them on a single curve. Okay, what you may do is okay, you may pick the terms, okay, you may pick the terms which are negative. Okay, you may pick the terms which are negative, and you may pick the terms which are positive, and they will independently lie on two different exponential curves. Okay, they will definitely lie on two different exponential curves, but not we cannot have a curve passing through all of them expressed as an exponential function. Okay, expressed as an exponential function. Take it. Okay, fine. So that's it for GP. Now let us go to HP. So what is a harmonic progression? First we consider an AP. Okay, first we consider an arithmetic progression. First term is A, common difference is D. Okay, and we assume that none of the terms in AP is 0. Okay, none of the terms is 0 or all is okay. It can be 0. It can be 0. So we say Tn is equal to A plus n minus 1 times D for AP. We define HP as we define HP as 1 upon Tn of corresponding AP. Okay, so for example, if I take my first term as 2 and the common difference is 3, what will be AP? AP will be 2, then 5, then 8, then 11, then 14, then 17 and so on. Okay, what will be the associated harmonic progression? Take reciprocals of all the terms. 1 by 2, 1 by 5, 1 by 8, 1 by 11, 1 by 14, 1 by 7 and so on. Okay, so if the terms in AP are there, then their reciprocals form harmonic progression and vice versa. If we have terms in HP, none of them is 0, we can take the reciprocals, then we are going to get an AP. Is this clear?
Yes, sir.
Yes. Okay. Harmonic. Now let's go to harmonic mean. Do you people know how to find harmonic mean of terms?
No, sir.
Okay, I'll define it. See, we know, what do we know? We know arithmetic mean. Okay, arithmetic mean is sum of the terms upon total number of terms. So to define the harmonic mean, I think I told you this when we were discussing statistics, but anyway, I'll mention it again. To calculate the harmonic mean, what do we do? We first take the reciprocals of all the available numbers. Okay? Then we add them and then divide the sum by the total number of terms, and again we take its reciprocal. Okay, again we take its reciprocal, we get the harmonic mean. For example, suppose we have two numbers x and y and assume that both of them are positive. What will be their arithmetic mean? X plus y by 2. What will be their geometric mean? You know that, it's root xy. And what will be the harmonic mean? Pay attention. 1 upon x plus 1 upon y divided by 2 raised to negative 1. Is that clear?
Yes, sir.
Yes, very good. So that's the harmonic mean. Okay, these terms need not be in AP to define their arithmetic mean. Similarly, the terms there need not be in HP or harmonic progression to define the harmonic mean. Okay? Alright. That is the harmonic mean and harmonic progression. Now, we do not, at least at this level, have a simple formula for sum of first n terms of a harmonic progression, because that is a very tedious job. Because for harmonic progression, Tn becomes, you can find the nth term, by the way. It will basically be the reciprocal of the corresponding nth term of an AP. But for the formula for finding the sum of first n terms, well, unless there is a pattern, observable pattern, we cannot do anything, okay? Except for using brute force method to calculate the sum, essentially summing all the terms using a calculator. Okay. Yeah, so this small discussion in the red color will head us to the famous arithmetic mean, geometric mean inequality. So this inequality says that suppose we have two positive numbers, x and y. The arithmetic mean is the greatest, followed by the geometric mean, followed by the harmonic mean. Okay, followed by the harmonic mean. Now let's simplify this a bit. Let us simplify this a bit. Numerator will be x plus y upon xy. Denominator will be 2 raised to negative 1. So this is 2xy upon x plus y. That's the harmonic mean. Okay. So AMGM inequality says that x plus y by 2 is the greatest, followed by root xy, then followed by 2xy upon x plus y. Okay, so AM is the greatest, then we have GM, and then we have HM. And if x is equal to y, that of course doesn't make any sense, then equality holds. That is, x plus the arithmetic mean becomes equal to the geometric mean becomes equal to the harmonic mean when x and y are equal. Is that clear? That's simple. Okay.
Yes.
Achha, one more thing. A, G, H are also, okay, let me put it in this way. If X, G, Y are in GP, then AM, GM, HM are also in GP. Now that is interesting, we didn't expect that. Let's check it for some numbers. We can prove it also. Let's check it for some numbers. Suppose I take X as 5 and suppose I take Y as 9. Right? So what will be AM? 7. What will be geometric mean? Root 45 or 3 root 5. What will be harmonic mean? 2xy, so 90 upon x plus y, 14, 45 by 7. Now I would like to square GM. That is 9 into 5, so that is 45. And I'd like to take the product of AM and GM, that will HM, that will confirm if equal that GM is equal to root of AM plus HM. That's 45 also. Again, 7 into 45 by 7, that's 45. So G squared is equal to AH or GM squared is equal to AM into HM. That is another useful result in solving the problems. See, basically this result is helpful when the numbers are not given but geometric mean and let's say arithmetic mean is given and you have to find the harmonic mean. Ideally the procedure would be from geometric mean and arithmetic mean, find the two numbers x and y and then apply the formula 2xy upon x plus y. But if you know that result, that G squared is equal to H, harmonic mean can be determined very easily by squaring the geometric mean and dividing it by the arithmetic. Okay, so that formula, let me write it here in case if you forget. Useful to calculate any mean from other two means without requiring the numbers to be found out. Is that clear?
Yes, sir.
Yes. Yeah, that result is important, might be helpful. Okay, yeah, okay, again, this result is applicable only when x and y both are positive. Okay, if they are of alternate signs, then xy becomes imaginary, and if they become negative, again the question comes like, what root should we take? Should we take the positive root or should we take the negative root? Usually when we take the square root, we take the positive root, correct? So we usually specify this result only for positive. Okay, that g squared equal to ah part also obviously becomes applicable for positive values of x and y. You can see what happens if you take one of the values as negative. Okay, see, because it is an equation, unlike the MJM inequality, you expect that even if the numbers there become imaginary or complex, that equation should still be applicable because it is an algebraic equation, right? It applies, okay? Not necessarily x and y have to be positive, even if they are negative. G squared equal to ah also is always applicable. Okay, fine. Yeah. There is another result that, if you know, could be better, but I'm not insisting you to remember this. If A, G and H are arithmetic, geometric and harmonic means respectively between three given numbers A, B and C, then the equation having the numbers themselves as its roots is x cubed minus 3ax squared plus 3g cubed upon hx minus g cubed is equal to 0. Okay, so this basically tells us that if we know the arithmetic, geometric and harmonic means, okay, by putting those things in this equation and then solving it for x, we can actually get the numbers. Okay, we can actually get the numbers. Okay. Okay, so I'm going to take an example and do it. So suppose I take the numbers as 2, let's take 5, and let's take the third number as 9. Suppose. So what will be the arithmetic mean? 14 by 3. It will be the geometric mean, cube root of 90, right? And what will be the harmonic mean? Harmonic mean will be 1 upon 2 plus 1 upon 5 plus 1 upon 9 by 3 raised to negative 1. Okay, let's find it. 0.5 plus 0.2 plus 1 upon 9. We have to divide this by 3 and raise it to negative 1. 270 upon 73. Okay, now let us form that equation. X cubed minus 3ax squared, so 14x squared, plus 3g cubed upon h minus g cubed, so that's 90 equal to 0. Okay, let's see now. If we solve this equation, we should get 2, 5 and 9. If we solve this equation, we should get 2, 5 and 9. Okay? See. 1, negative 14, 3 into 90 into 73 upon 270, negative 90. Okay, something is wrong in my calculations. Let's go back and see. 2, 5 and 9. Oh, my arithmetic mean itself is wrong. Sorry. It should have been 16. My bad. It should be 16. Okay, everything else has been calculated on calculator, so should be right. Okay. So I just need to change my B to negative 16. Yeah, see 952. 952. Okay, first root is 9, second root is 5, third root is 2. Okay? Well, you may remember that if A, B, C are the roots of any cubic polynomial, then that polynomial is given by x cube minus a plus b plus c x squared, right? Plus ab plus bc plus ca x minus abc. So essentially they have made use of the same thing here. Look, g cube is after all what? The product of the numbers, because if we take the cube root, then you'll get the geometric mean. Okay? And why this 3a here? Why 3a here? Because if we take the sum of the roots, right? That sum is actually the coefficient of x squared divided by the coefficient of x cube. We know that. And what is a plus b plus c upon 3? That's arithmetic mean. So 3 times arithmetic mean is that. You can do a bit of mathematics, a bit of simplification to arrive at this result, 3g cubed upon h. That's even visible here also. Look, 3g cubed is how much? 3 times ABC. Okay, 3 times ABC. And if you divide it by the harmonic mean, here we have to use the harmonic mean of 3 numbers formula. You will get that. Okay. If you want, you can try it. I think you should try it. Okay, it's a good homework exercise. Is it clear what you are supposed to do?
Yes, sir.
Yes? Okay. Great. So that's it for arithmetic, geometric and harmonic means. Now, have you people heard of this progression called AGP?
Yes, sir.
Okay, I think in NCERT it's not there. Or is it? Arithmetico-geometric progressions. It's essentially a combination, a composition of the two progressions. And I think this AGP was asked in one of the old JEE main examinations, which was named as IIEE in my days. It was called IIEE, All India Engineering Entrance Examination. There was a question, I don't exactly remember, but that question was on this particular progression. I'm just going to discuss the structure of it. I'm not.
Sir, they have removed this topic for JEE this time.
They have?
Yeah.
Included?
No, removed.
Okay, removed. Okay. Okay, let's just go through the concept then. See, anyway, this topic is not very frequent. And even if they ask a question on this, you should be able to recognize the pattern. That's it. Everything else should be just your knowledge of mathematics, because I don't think they expect you to even memorize this formula. S infinity a upon 1 minus r plus dr upon 1 minus r bracket squared. I don't think anybody is going to ask you question testing your memory on that. But let us just try to understand the structure of it. Okay, structure of it. So in AGP, what do we do is, we first take the arithmetic progression. We first take the arithmetic progression and then we multiply the terms of this AP by corresponding power of r. That is AGP. Remember, don't take r first. Okay, it won't then remain either AP or GP also. Please take first the common difference. So A comes first. So first arithmetic and then geometric. Multiply by r. So A plus dr, A plus 2 dr squared and so on. That is the, okay. So if I want to write the nth term here, what should I do? First nth term of AP, then r raised to n minus 2. Okay. Alright. Not recommending this to memorize this formula, but take a look at this S infinity formula. This of course is valid only when common ratio is less than 1. The absolute value of common ratio is less than 1. Okay. So it is a upon 1 minus r. This term is there. That is S infinity of GP. Right. That is S infinity of GP. And then it is a dr upon 1 minus r squared. So that d comes from the common difference part. Okay. You can prove it, but Not recommending you to memorize. Just remember the basic. Okay, the definition. Alright, let's now go to the last part. Important formulae. Sum of first n natural numbers, n into n plus 1 upon 2. Result provable using induction. Right, you can prove it. Try to prove it as an exercise on mathematical induction. J squared, a bit complicated. Sum of squares of first n natural numbers, it is n into n plus 1 into 2n plus 1 upon 6. Okay, so it is n into n plus 1 upon 2. That's the previous formula. Into 2n plus 1 upon 3. Okay, and for j cube it is square of the first. N squared into n plus 1 squared by 4. Now, apart from questions on summation notation itself, where are these formulae useful? Have you ever thought about that? These formulae are useful when we go to definite integration as limit of a sum. Okay, when we go to definite integral as limit of a sum. For instance, if I integrate x, I get x squared by 2. So that square term here has a special significance. If you measure the degree of the numerator, that is also 2. Okay, that is also 2. Here if we take x squared and integrate it, we get x cube upon 3. Well, forget the constant of integration. And if you measure the degree in the numerator here, of the numerator, n plus 1, so n squared, and then I get 2n, so that's again n cube. Same thing here. Integral x cubed is x raised to 4 upon 4, and that is again reflected in the product of n squared at this n squared. That's n raised to. Okay, so useful not only in problems on summation notation, but also useful in definite integral as limit of a sum examples. I think this definite integral as limit of a sum has also been removed from NCERT syllabus this year. Am I right?
Sir, they've removed from JEE, so these formulae.
But I don't understand what is the reason to remove that? They could have removed something else also. Because in physics we use it. In physics, whatever integration we use, that's definite integration. Like when we say f bar dot dx bar, why are we doing f bar dot dx bar? Because f bar is not a constant, that means it is a function of x. Right? So when we use this, it's definite integral limit of a sum. And yes, let's leave that. Okay, fourth, this is another resemblance between summation and integration. Summation is a linear operation, which says I can take a outside, I can sum things up, and then I can just get this b. But don't forget that this b is to be multiplied by n. Right? That b is to be multiplied by n. Why? Because this is inside the summation. Okay? So summation b just tells me add b as many times as the numbers here. So here it is, we want to add b n times, and that n at the end is a consequence of that. This n is important. So it's not just a into this plus b. No, that's not the case. Okay? And this is also applicable with the integral also, isn't it? So if I have integral a f of x plus b dx, the integral tells me integrate f, but while integrating b, multiply by x. Okay? So summation and integration both are linear operations. Although in integration we have continuous functions, or functions defined on the real numbers, and here we have discrete functions. Okay, fine. Last part, power series expansions. This you will find in the appendix. Okay, these power series expansions come from a theorem called Maclaurin's theorem. It's there. Okay, it's no big deal. It's there. But proof of Maclaurin theorem involves mean value theorem. Okay. Now I'm recommending you to use these, memorize these results, because well, knowing these results I think can be beneficial. I'll tell you how. Look, for e raised to x it is 1 plus x squared by 2 factorial plus x cubed by 3 factorial and so on. Okay. Now the significance of these results is that if x is very small, but positive, then we can actually approximate e raised to x as 1 plus x squared by 2. Okay, we can use that approximation. So we can actually replace e raised to x by a quadratic function. It's not true. Okay, they do not overlap exactly, but for the sake of calculations that might be useful. Okay, sin x is x minus x cubed by 3 factorial. I'll also tell you where we have used this result, plus x raised to 5 by 5 factorial minus x raised to 7 by 7 factorial and so on. Okay, fine. So here you understand that if x tends to 0, what happens to sin x by x? If we divide both sides by x, okay, this tends to 0, or this tends to 1, or that this becomes 1 if we first go to this side, if we shift x here, not in the numerator but in the denominator, if we divide both sides by x, then we can see clearly that sin x upon x becomes 1 minus x squared by 3 factorial plus x raised to 4 by 5 factorial and so on. So now if we take the limit, we know what to do on the right side. On the right side everything is 0 except this one, and hence that limit. Also, if x is very small, these terms can be ignored and sin x can be approximated as x. In simple pendulum's derivation and considering it as an approximate simple harmonic motion, we have made use of this approximation for simple pendulum, if you remember the derivation. So many things in physics actually depend on these small approximations or these small things which, if not told in the right way, may lead to some confusion. Okay, but I think now I made it clear. Let me also write it. We use this approximation. We use this approximation in derivation of simple pendulum. Okay, fine. For cos x, it is an even function, so we expect only even powers to be there. Okay, this is it. Now another feature of these functions is that, or these power series expansions, is that they also give us the derivatives. Correct. Look, if I take the derivative of sin x, I'll get cos x. Now look at the derivative of x, it is 1. What will happen to derivative of x cube? 3x squared. That will cancel that 3. So it will be x squared upon 2 factorial. What will happen to the derivative of x raised to 5 upon 5 factorial? It's 5x raised to 4 upon 5 factorial. 5 will go, again 4 factorial will remain. Okay? So I'm recommending you to memorize only first and the second. The remaining things will automatically fall at the right places. Is that clear?
Yes, sir.
Yes.
Yes. Okay. Last two. Now this is something that we have already derived. Remember that from the GP part. This is 1 plus x plus x squared, exactly. And then if we go to 1 upon 1 plus x, then you have to replace x by negative x. So positive powers, even powers remain positive, odd powers acquire a negative sign. Okay, but that's not it. But last thing I want to tell you, we can actually integrate this. We can actually integrate this. Okay. And this will actually serve as the power series expansion for log of 1 plus x. Let's see. Let's go to log 2. Okay, need to check whether the convergence is there, but let's see if the convergence is approximately 0.69, right? Length 2 is approximately 0.693. Now let's calculate that using this. Okay, so it's 2 minus 2 plus 2 by 3, plus 8 by 3. Okay, no, it's not getting, because this region of convergence here is only when mod x is less than. Okay, I think we can go for ln 1 upon 2. Right, we can, it's negative 0.693. Okay, so let me store the answer as half. So answer minus answer squared by 2. Okay, plus answer cube by 3. Okay, well, let's take one more term, minus answer raised to 4 by 4. Wait. I think I'm making a mistake here. So by doing this, we are getting log of 1 plus x. Yeah, okay. Log of 1.5. Sorry, my bad. Log of 1.5. That's 0.4054. And this thing that we had calculated, 77 upon 192. That is also around that. Okay. 0.4054. 0.4010. That's fairly accurate till corrected till 2 decimal places. I think we can also find ln2 from that. Here I should have taken x as 1. Let's see if by taking x equal to 1 it works. It's even easier now, right? It's even easier. 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4 and so on. 7 by 12. That's 0.583. So if we consider a few more terms, it will definitely converge to 1 or at least get closer and closer to 0.693. Okay. Alright, so those are the things that I wanted to tell you, apart from the standard things that we study in sequences and series. So for 1 upon 1 minus x, I don't see any problem, because that is GP part, GP itself. And then for this e raised to x and sin x part, I am recommending you to learn them, e raised to x and sin x. It could be useful in any sum. I'm not sure how exactly, but please remember them. Anyways, in your higher level, higher standards, you will be required to know it. Okay? Fine. So that's it for sequences and series theory. In our next lecture, we will solve the MCQs. Okay? If you still have any doubts, or if you did not understand anything that we explained or I explained to you today, please ask me. I will make sure that you understand it correctly. Permutations and combinations. Okay, permutations and combinations. Now these two operations are so important. Okay, these two operations denoted by NPR, a special case of permutation, and NCR. These operations are important and they find separate keys on scientific calculator. I will show you. When we were discussing binomial theorem, I think we have used these keys. Okay, there is this NPR written here, NPR and NCR written above these keys. Okay, above the into and division thing, you can see NCR and NPR. So I can find them right here. If I wish to find 6P2, I can find it here. If I wish to find 6C2, I can even do that here. Okay, so that functionality is available. But anyways, so important. These things are important. Okay, these things are important in counting. These are important in binomial theorem. These are important in binomial distribution. These are important in finding number of subsets of a set and so on. Okay, there are many applications. I made a list of those applications, some of them at the end of our theory discussion. Okay, fine. Acha, so let us discuss three counting principles. So these counting principles are indirect ways of counting. Okay, please remember that. Indirect ways of counting. So in solving any counting problem of present era, if we continue to count, then it will take us forever. Okay, and therefore we have developed these counting principles which will help us, or which do help us in solving a problem in smallest possible time. And if we give it to a computer or a calculator, even the calculation part is not required to be done manually. Okay, first, pigeonhole principle. Okay, what does pigeonhole principle tell? So going by its name, it basically says that if there are m holes, okay, if there are m holes and n pigeons with number of pigeons exceeding the number of holes, then at least one hole has more than two pigeons. Okay, more than two pigeons. Now what are some interesting applications of this? Okay, applications, example first. Suppose there are 13 people. Okay, there are 13 people in a group. At least two of them will have same birth month. Okay, at least two of them will have same birth month. Why? Because number of months is 12. 13 people, so two people have to have same birth month. Have you understood this? It has to be there. We don't know what month will it be and which two people will have the same birth month. It can also not also be always true. Even multiple people can have same birth month. Okay, and in a group of 366 people, what can we say? At least two of them will have same birth date. Or I would say birthday instead of saying birth rate, etc. Is it clear? Pigeonhole principle application.
Yes,
And there are other applications also, like for example, if you consider the population of non-bald people on earth, at least two of them have same number of hair. Why? Because we know what is the maximum number of hair that a person can have at a time and the population exceeds that. So without even verifying, we can prove that there are at least two non-bald people which will have the same number of hair on their head without counting. So that's the way, indirect ways of counting. Okay, indirect ways of counting. That's the pigeonhole principle. Let us now go to addition principle. Okay, addition principle is very simple. Okay, what is addition principle? Let us consider some examples because you people may already be aware of addition principle. Okay, so suppose you have 5 t-shirts and 4 formal shirts. And if we have to pick either one shirt or either one t-shirt or one formal shirt. Okay, well, how many ways can we do that? Number of ways is 5 plus 4, and we naturally add them, we don't even think about it. Okay, 5 plus 4, so 9 ways. So when you frame the situation in either or, using either or, then the addition principle is at work all the time. It's not always the two cases. Suppose we have 5 t-shirts, 5 formal shirts, and let us say something else. Okay, in how many ways can you do that? The number of ways will be just simple addition of all of them. Now I will not tell you the addition principle in words, right? You understood the concept. Or shall I do it again? Or shall I explain it?
Understood.
Understood? Okay, addition. Understood. Very good. Addition principle. Okay, now there is a theorem associated with this in probability. We call it addition theorem. We've seen that. Okay, addition theorem of probability is there where we add the probabilities. Okay, and usually addition theorem is at work when we have union of two sets. Okay, we have union of two sets. Fine, and in fact, if you remember logic gates from physics, although we have not yet discussed them, there is a gate called OR gate. And in OR gate we implement logical addition. Okay, we implement logical addition. If you have had computer science in your 12th standard, bifocal subject, you know.
Yes, sir.
Okay, you know what I'm talking about. Okay, addition. So addition, union, those are related. Either or. Three. Okay, so three keywords are important: addition, either or, and union. Okay, union. Okay, similarly we have multiplication principle. Okay, so we indirectly apply, knowingly or unknowingly we apply the multiplication principle. Okay, suppose we have 5 t-shirts. Okay, suppose we have 5 t-shirts and let us say 6 trousers. Without worrying about the color combination, in how many ways can we select one t-shirt? Okay, in how many ways can we select one t-shirt and one trouser? We know now how to do this. Okay, if we select first t-shirt, it has 6 possible combinations of trousers, correct? Second same, third same, fourth same, fifth same, so addition becomes multiplication now. So it will be 5 into 6, so number of ways will be 30, 5 into 6. Number of ways will be 5 into 6, so that's it. The answer is not important, the way we find it is important. Again, indirect counting is what we are doing, we are not directly counting. Well, we did that because the numbers 5 and 6 were small, but as we shall see in MCQs, those numbers won't be small. We need a very sharp brain, a computer brain to actually solve those problems. And if you have computing power, enough computing power, what you can do is you take any permutation combination problem at this level, you can solve it using a computer within fraction of seconds, assuming that you program it correctly. No calculation required, nothing. Just feed the information, it will do it for you. Okay, but well, we have to do it manually. Okay, so that's multiplication principle. Now, like we had these similarities for addition principle, we also have similarities with multiplication principle. Okay, so here we have got multiplication theorem. Okay, here we have got multiplication theorem, which gives us the intersection probability. Okay, intersection probability. And in logic, okay, here we had OR gate and here we have got AND gate. Okay, here we have got AND gate, and AND gate implements logical multiplication. Okay, AND gate implements logical multiplication. Sorry, I should have used blue color here. to be consistent with the scheme. Okay, so multiplication principle is when you frame your problem or your solution is this and that. So when it is and, then we multiply. Okay, it is usually intersection and logical multiplication and. Okay, don't forget the three words: multiplication and intersection. Okay, multiplication and an intersection, addition or and union. Okay, addition either or union, multiplication and intersection. Okay, all right. Now everything is based on these three principles only. Okay, factorial notation. Quick revision of factorial notation. Okay, we define for all n belonging to the set of natural numbers n factorial as 1 into 2 into 3 up to n fact up to that's n fact. Okay, additionally we define 0 factorial equal to 1. Additionally we define 0 factorial equal to 1, and well, we can also prove why 0 factorial is 1, but let's not go into that. And there is this recurrence relation, because if you see, factorial notation is a function whose domain is a set of natural numbers, so it is actually a sequence. Okay, it is actually a sequence and therefore a progression. So if we call an as n factorial, I can say that an plus 1 is equal to n plus 1 into an. Okay, that is the recurrence relation for factorial notation. We have similar relationships. An plus 1 is equal to an plus d for ep, and an plus 1 is equal to an into r for gp. We have had that. Okay, so that's a similar recurrence relation for factorial notation. Okay, I will not tell you other properties. You people already know factorial notation property and properties. The only definition is important, right? 0 factorial is 1 and that n factorial. Okay, now let us discuss permutations part. Do you people know the difference between permutation and combination? In permutation, order order in which we arrange the objects is important. In combinations, the order is not important. If you do not, let me just write it here. Permutation is an arrangement of objects. But so is combination. Combination is also an arrangement of objects. But then what is the difference? In permutation, order matters. Okay, order of arrangement matters. And in combination, order of arrangement does not matter. Okay, that's the basic difference. You know this, right? The basic difference between permutations and combinations. Okay. First, number of permutations. We have n distinct objects. We take r objects at a time and the repetitions are allowed. Now if repetitions are allowed, then what is the formula for number of permutations? Okay, if we take r objects at a time, repetitions are allowed. So every time those n choices are available. So for the first place, if we say, for the first place, how many options are available? N. For the second place also there are n objects available because repetitions are allowed, and therefore the total number of permutations will be n into n into n r times. So that is n raised to r. Okay. But if you have n distinct objects taken r at a time where repetition is not allowed, then this per number of permutations decreases. How does it decrease, or why does it decrease? Danish, what happened? Do you have any?
I misclicked, sir. I misclicked.
Oh, okay. Now in the second case where I am saying that the repetition is not allowed, for the first place there are n options available, but for the second there will be one less option available because you chose an object and you put it there. So the number of permutations here will be n into n minus 1 into n minus 2, and how far should we go? We should go till r places. Okay, till r places. Now look, for the second place it is 1, for the third place it is 2, so for the rth place it will be r minus 1. Okay, and you can use properties of factorial notation to get this as n factorial upon n minus r factorial, and that is what we call NPR. So NPR is not the only permutation that is possible. NPR applies when we have distinct objects and when we prohibit the repetitions. If we prohibit the repetitions, then NPR works. If we do not prohibit the repetitions but still consider distinct objects, then it is n raised to r. Okay, so two formulae, both are permutation formulae, and there are few more coming up. First, suppose we have n objects and we have to take all at a time. Okay, suppose we have to take all of them, but here there are some objects which are identical. Let's say R1 objects are identical of one kind, R2 of another kind, and Rm of mth kind. Then what is the number of permutations here? It is n factorial upon R1 factorial into R2 factorial up to Rm factorial. Okay, you people know this, right? Also you can prove it. Okay, there is no big deal to prove it, but let's avoid the proof for the time being. Is it clear, the third thing in combination, permutation? Okay, great. Fourth is the case of circular permutations. There are n objects to be arranged in a circle and we are going to pick all of them at a time. And suppose we treat clockwise and anti-clockwise arrangements as different arrangements, then the number of circular permutations is n minus 1 factorial. Okay, because associated with every circular permutation there are n linear permutations. Okay, associated with every circular permutation there are n linear permutations or n linear LP, linear permutations LPs. Okay, and because the number of linear permutations is n factorial, if we divide it by n, then we get the number of circular permutations as n minus 1 factorial if we treat clockwise and anti-clockwise different. If you treat clockwise and anti-clockwise as same, then it becomes n minus 1 factorial divided by 2. Okay, it becomes n minus 1 factorial upon 2. Okay. Yes. Oh, okay, okay, good. So suppose we have 4 objects. Okay, wait, I have it here. Yeah. So suppose there are 4 people, A, B, C, D, and there are 4 chairs available. Okay. Now we know that the total number of linear permutations will be 4p4 or 4 factorial, that is 24. Is it clear? Okay. Now the statement that I made, that associated with every circular permutation there are n linear permutations, this is what I meant. Okay. Suppose you consider the sequence A, B, C, D, that is one permutation. Okay, if you just follow the colors here you will get it. Okay, first we are starting with D, so DABC is one linear permutation, ABCD is the second, BCDA is the third, and CDAB is the fourth. Right, I hope you understood that. So you start from you start, let's say D sits on the extreme left position in linear arrangement, then A sits on the extreme left position, then B sits on the extreme left position, and C sits on the extreme left position, but in the circular permutation the sequence is ABCD. Okay, which means there are n different ways, 4 different ways in this case, to let the people sit in a row. That is a linear permutation. But if you make them sit round a circle, okay, round a circle, if you make them sit, then ABCD, BCDA, CDAB and DABC all sound similar. Got the point? That's the thing. Okay. Associated with every circular permutation there are n linear permutations. Fine. Okay, finally let's go to combinations. We know that in combinations the order is not important. So if we have n objects and we have to pick r at a time, what is the formula for NCR? Look. See, now just like the statement that we made here, that associated with every circular permutation there are n linear permutations, we can also make a statement here. And that statement is associate, oh sorry, not here. Yeah. Associated with every combination. Okay, associated with every combination of R objects, there are R factorial different permutations. Is it clear? Because those R objects, in how many ways can you arrange them? R factorial ways, considering order is important. Which means if we multiply total number of combinations by R factorial, we will get NPR, and that gives us NCR as NPR upon R factorial, which is n factorial upon R factorial into n minus R factorial. Okay, is it clear? Number of combinations? Okay, so NCR is equal to NCN minus R. That famous formula follows from this. Okay, there are also other formulae related to combinations. And I've not included them here. I will send you the PDF of that later. Okay, or remind me. Formulae of combinations. Which formulae? These mathematical formulae. Okay. Okay, formulae on NCR. Okay, see, like you people must be knowing this, that NC0 plus NC1 up to NCN is 2 raised to n. Do you know this? That comes from binomial theorem. That comes from binomial theorem when a and b both are equal to 1. Okay, and then this has very nice applications. Like if we have a set of n elements, how many elements can or will its power set have? It's as good as picking no object from n, or no element, that's 1, and 1 element, so n, then nc2, 2 elements and so on. Okay. Alright. Now here are some common situations involving counting principles and their extensions, permutations and combinations. First one is handshaking lemma. Handshaking lemma tells us that if there are n people, okay, and suppose they shake hands once with each other. Okay, shaking hands with each other. Now you understand that this is a combination, because I shaking hands with Rajat is as good as Rajat shaking hands with me, right? So this is NC2. That is n factorial upon n minus 2 factorial, n minus r factorial into r factorial, or it is n into n minus 1 upon 2. Okay, that is handshaking lemma. Please note that this is not n into n plus 1 upon 2. This is not summation k as k goes from 1 to n. that is n into n plus 1 upon 2. Okay, well you can say this is n plus 1 c upon 2, right? This is n plus 1 c upon 2. Okay, but that is not NC2. Okay, that is handshaking lemma. Second, number of triangles in a plane. So what are given point things? Suppose there are n non-collinear points. Okay, there are n points. Okay, let me do it in this way. N points. No three are collinear. Then how many triangles can be constructed? NC3 triangles. Because then the problem becomes picking 3 points out of n points, and we know that if we have any 3 non-collinear points, then we'll always get a triangle. Okay, now if, often the problems are not so straightforward. We will see them today or whenever we solve the problems, that well, let's say some of them are collinear, some of them are not. In some cases points will lie on 2 lines only or 3 lines only. So how to pick the number of triangles, we will see that soon. Okay, but is it clear NC3? Why is it NC3?
Yes, sir.
Okay, great. Third, number of diagonals of a polygon. Okay, this is also another standard combination exercise, number of diagonals of a polygon. Okay, so suppose we have a polygon which has n vertices and therefore it has n sides. Now how many diagonals will it have? If we pick any 2 points out of those n, then we will get line segment joining them. So there will be NC2 segments, but these NC2 segments cover the diagonals as well as the sides. So it will be NC2 minus n. Okay, number of diagonals of a polygon is NC2 minus n. Okay, that NC2 represents sides plus diagonals, n sides because there are n vertices, so that will go. Acha, there is another thing. Yes. You didn't understand. Okay, look. Let us say that you have a heptagon. 2, 3, 4, 5, 6, and 7. So suppose n is equal to 7. Okay, so this is also equal to 7. Now suppose you go to this point. With how many points can you join this point with? 2, 3, 4, 5, 6. Is it clear? 6. Now let us go to, suppose you go to the next point. How many options do you have now? You can't come back to this. Okay, so how many options do you have? 5. Okay, now suppose you go to this. How many options do you have? 4. Suppose you go to this. How many options do you have? 1, 2, 3. Suppose you go to this point. How many options do you have? 2. Correct? And then into 1. Is it clear?
Yes, sir.
Okay, so this is actually 6 factorial. Okay, let's go to 7c2 now. Wait, 7c2 will be 7 factorial upon 2 factorial into 5 factorial. Wait, I think I have made a blunder here. This has 6 options. 1, 2, 3, 4, 5, 6. Okay, that's right. Okay, I think I have forgotten to wait. Okay, I should have added these. Wait. Why am I multiplying? Because I want to count the total number of segments, right? I'm not considering the, well, multiplication. Addition makes sense here. Okay, so it is either this or this or this or this. So we want to add them, right? Sorry, I should not have added them. So that's the total number. 6 plus 5 plus 4 plus 3 plus 2 plus 1, right? And that is 21, because if you use the formula, it is n into n plus 1 upon 2. So that is 42 by 2. So that's 21. That's NC2. But out of these 21, 7 are the sides, correct? 7 are the sides. So how many diagonals will it have? 14. Clear?
Yes, sir.
Now you can also approach the problem by not considering the adjacent vertices, but that becomes more complicated. So you can just use NC2 minus N3. And my bad, I did not apply the multiplication, addition principle correctly here. It's OR thing, right? So OR means addition. Okay. Is it clear now? Number of diagonals?
Yes, sir.
Okay. Okay. Yes. Number of factors of a natural number. Now this is something which we do not often discuss. Number of factors of a natural number. Now this comes from a theorem which tells us that every natural number, okay, every natural number has a unique prime factorization. Okay, has a unique prime factorization. For example, suppose I consider 120. Okay, suppose I consider 120 and I know that it is 5 factorial. That's why I chose it. Okay, it is 5 into 4 into 3 into 2 into 1. Okay, so 2 is coming thrice in 2 and 4. 3 is coming only once and 5 is also coming only once. So 8 into 3, 24, 24 into 5, 120. Okay, so when we take this particular combination, 2 raised to 3, 3 raised to 1 and 5 raised to 1, we are only going to get 120 and nothing else. Have you understood this? Okay.
Yes, sir.
Now, every factor, okay, every factor of 120 is going to have some power of 2, some power of 3 and some power of 5. Okay. Every factor of 120 is going to have some power of 2, some power of 3 and some power of 5. And what is the range here? 2's power cannot be greater than 3. It can be 0. So it is 0, 1, 2, 3. So it can be either 0 or 1 or 2 or 3. So there are 4 ways. Okay. And for 3, how many? There is only one power. So 3's power can be 0 or 1. So 2 ways. And what about 5? Also it can be 0 or 1. So there are 2 ways. So how many factors are there? 16 factors are there. Okay. 16 factors are there. Okay. So okay, if possible, you can just make a list. 1 is there, 2 is there, 3 is there, 4 is there, 5 is there, 6 is there, 8 is there, 9 is not there, 10 is there, and 12 is there, right? And 24 is also there. Is 36 a factor of 120? No, right? Let's also start writing in the descending order. 60 is there, 40 is there. Okay, are there any other factors? 30 is there, right? 30 is there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, we are missing 2 more. What are they? 16 is there. Yeah, 20 is there and 16 is also there. Is 16 divisible, is 120 divisible by 16? So, no, okay, no, 16 is not. Okay. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, which one are we missing? 2 into 60, 3 into 40, 4 into 30, 24 into 5, 20 into 6, 12 into 8, 10 into 12. Oh, are they 16? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, there is one more that I am missing. 15. Yes, 15. Okay, so that makes it 16. And now you understood how complicated can it be even if we miss one of these factors. So it's better to have a systematic way. Okay, it's better to have a systematic way. So let's say the given natural number n is factorized into primes. Suppose it has p1 raised to k1, p2 raised to k2, and suppose it has pm raised to km. Then how many factors will it have? k1 plus 1 into k2 plus 1, because 0 comes, k3 plus 1, and so on. Okay, up to what? Km plus 1. Is it clear now? Yeah, there is also a formula to calculate the prime power in n factorial. You can just take it as homework. Number of powers of a prime p in n factorial, and it's given by n by p box greatest integer function plus n by p squared. It's not n factorial, by the way. You have to continue this until you get 0. Okay. You can prove it. Take it, otherwise I'll explain it later. Okay. I don't think they will ask you this, but who knows. Fine. The last is number of matrices with specific entries. They can also ask you this. Okay. So if I say that my matrix is of the order m cross n, okay, and the cardinality of the set of elements is p. So in how many ways can we build a matrix? The number of ways is p raised to mn. Why p raised to mn? You got the point. Okay, look. Suppose I want matrices which contain only 1, 2, 3, 4 as their entries, and suppose the matrix is of the size 7 by 8. So there are 56 places to be occupied, and we know that for matrices it's like a permutation. Matrix is like a permutation, so order is important, right? So for the first, how many options I have? 4. For the second, I have 4 options. So 4 into, and there are 56 such ways. So 4 raised to 56 or 4 raised to 7 into 8. And then you can put some restrictions here, like how many skew symmetric matrices will be there, how many symmetric matrices will be there, and so on. Okay, is it clear? Yes. And you can come up with other problems also. Okay, like a number of subsets. Then number of, essentially same problem, number of relations, number of functions, then number of injective functions, number of surjective functions, number of 1, 1 function, okay, number of invertible functions, and so on. Okay. Alright, so these are some other things that I can recall where permutations and combinations are involved. If you know more, then we can add them in the list, let me know. Well, let me ask you one question. Why do we study these two topics together? You go to any state board textbook, if you go to NCERT, they always combine mathematical induction with binomial theorem. Why is that? Any idea? Why do we study binomial theorem and mathematical induction together? Yes, correct. That's the only reason. The proof of the binomial theorem is due to principle of mathematical induction. Okay, so what does binomial theorem state? Yeah, states let A and B be any two real numbers. Okay, suppose A and B are any two real numbers, and suppose n is a natural number. Okay, suppose A and B are real numbers and n is a natural number. Then A plus B raised to n is given by NC0 A raised to n B raised to 0 NC1 A raised to n minus 1 B raised to 1 plus NC2 A raised to n minus 2 B raised to 2, so on. Can anyone please tell me the general term? NCR A raised to n minus r B raised to r. And what will be the last? Okay, let us first write down the second last term. Okay, anyone with the second last term? NC n minus 1 A raised to 1 B raised to n minus 1, and it concludes with NCN A raised to 0 B raised to n. Is everybody familiar with this?
Sir.
Okay. Everybody is familiar with this. Okay. Now, just make it more complete. Let us write down what is NCR. N factorial upon r factorial into n minus r factorial. Okay, NCR is that. So sometimes in some books they use NCR, they write it as, it's not a fraction, okay, because the horizontal line in between n and r is missing, but that is still combination. Okay, combination NCR. Okay, let's write down few more simple results. Number 2. How much is NC0? 1. How much is NCN? That is also 1. NC1 is n, and NCN minus 1 is also n. And this is because of the following property of combinations. NCR is equal to NCN minus r. Do you people know this property? NCR equals NCN
Yes,
minus
sir.
r? Yes, okay. Fine. How many terms are there in the expansion? If n is a natural number, then a plus b raised to n has how many terms? N plus 1 terms. Okay, how can it have n plus 1 terms? Because see, NC0, NC1, NC2 up to NCN. So if it had been NC1 to NCN, there would have been n terms. But it additionally has this NC0 thing. So it has n plus 1 terms in it. Okay, it has n plus 1 terms. Okay. General term, we call it r plus 1th term. Okay, how do we write it? NCR A raised to n minus r B raised to r. Okay, that's the central term here. This term. NCR A raised to n minus r B raised to r, that is the general term. You know it, right? General term? Okay. Sum of the binomial coefficients. Okay, so what are the binomial coefficients? NC0, NC1, NC2, NC3 up to NCn minus 1 plus N. These are all binomial coefficients and their sum is equal to 2 raised to n. Do you know this or not? You did? Okay. See, it's very easy. If in the statement of binomial theorem, suppose you let A as 1 and suppose you also take B as 1. then will LHS not be equal to 1 plus 1 raised to n or 2 raised to n? Right, LHS will be equal to 2 raised to n. And on RHS, because A and B both are equal to 1, it is never going to matter what powers of what powers are there for A and B, they both are 1. So NC0 plus NC1 plus NC2 so on till NCn, that addition becomes equal to 2 raised to n. Is that clear? Huh. Now this takes us back to our discussion on sets and relations, and there we say that number of subsets, or let me say number of elements of power set of A is 2 raised to n if cardinality or size of A is n. Now why does that work here? That works because NC0 is the number of ways of choosing no elements out of n, so that's 1. NC1 means number of ways of choosing one element from n, that is n. NC2 means number of ways of choosing two elements from n, that means those subsets of A which have only two elements in them, and so on. So the proof of the fact that if set A has n elements in it, then its power set is going to have 2 raised to n elements, or it will have 2 raised to n subsets. The reason, or one way to prove it, is first to know mathematical induction, then to know binomial theorem, and then substituting or using a special case A equal to 1, B equal to 1 to get that result. Okay, so remember this, sum of binomial coefficients is always 2 raised to n. Have you followed this? Okay. Fine. Any illustration where we use binomial expansion in physics? Come on. Where do we use binomial expansion in physics? Yes? But in what specific context?
Can't remember.
Okay, I'll leave it to you. You are supposed to tell me where we use binomial expansion in physics. It's rather binomial approximation, I would say. Okay, see.
Gravitation.
Yes, gravitation, correct. Variation of acceleration due to gravity. Okay, I'll show it to you now. Quickly. Try to find it in NCERT. Variation of G with respect to okay, acceleration of due to gravity above and below the surface of the earth. Yeah, see. For h upon re less than or equal to 1 using binomial expression. Okay, using binomial expression. Right? So what exactly do we mean there? Okay. So usually in physics when we use binomial expansion, the index of that expansion is going to be a rational number or negative integer. Okay. If n is a negative integer, or okay, if n is not necessarily a natural number, okay, if n is not necessarily a natural number, then what happens to the expansion of a plus p raised to n? depending on our convenience, we either take A common or B common. So suppose I take B common, so it becomes 1 plus A by B raised to n. Okay, so we keep B raised to n as it is, and then it is 1 plus n into A by B plus n into n minus 1 upon 2 factorial into A by B squared. Okay, how do we continue writing this? Do you know? We continue to write this by using the formula. Okay, that NCR formula is there, but we can't use NCR there because n is not a natural number, not necessarily a natural number rather. Upon 3 factorial into A by B raised to 3, and so on. And it is going to continue because it is never going to end. Okay, it is never going to end. So this is called an infinite series. Okay, it is called an infinite series, and we use binomial approximation. Okay, now when we do not consider many terms of the infinite series, we give it a special name. We call it a truncated series. Okay, now if A by B is very small, we can ignore their squares. So we approximate it as B raised to n into 1 plus n into A by B. So we basically truncate everything that follows after this. Okay, we don't consider this. That is called a truncated series or truncated expansion. Okay, so we use it in acceleration due to gravity variation. One illustration of binomial expansion in physics. Have you understood this? Okay, please remember it. Okay, they may ask you to go till the second or third term, but not definitely beyond that. Okay, or fourth term max. Any doubt? Binomial expansion in physics? No doubt? Okay. Fine. Now let's try to connect binomial theorem with another topic from mathematics, that is sequences and series. Right? We know the following result from sequences and series, that suppose we have a geometric progression with first term equal to A and common ratio R, but the common ratio R is such that its mod is less than 1. Okay, its mod is less than 1. Okay, then what is the formula? Does anyone remember the formula for this? Sum to infinity is A upon 1 minus R. Is that formula clear? Do you know this formula? No? How is that possible? Oh, okay. NCERT में geometry progression नहीं है ना? Right? You don't have it, right? In NCERT?
Progression is there.
Oh, sorry, harmonic is not there. Harmonic progression, yeah. But then you should know this formula. The formula is, okay, I'll tell you the formula. The formula is, if I want to add n terms of a geometric progression, first n terms, then the formula is A into 1 minus R raised to n upon 1 minus R. Are you aware of this formula? Okay, so this is the NCERT formula. Okay, sum of first, sorry. By mistake I pressed a different key. See, this is the formula that I'm talking about. Okay, and if R is smaller than 1, or in between minus 1 and 1, its higher and higher powers are going to diminish very fast. So that brings us, that makes 1 R raised to n 0. So 1 minus R raised to n becomes 0. So S infinity is A upon 1 minus R. Okay. Now suppose I ask you to expand this 1 minus R raised to negative 1 using binomial theorem. What does it say? Okay, let us first write it as 1 plus negative R raised to minus 1. Okay, 1 plus negative R raised to minus 1. For my convenience, I have done that. So here, it will be 1 plus nx. Okay, so minus 1 into minus r plus n into n minus 1 by 2 factorial or 2 into negative r squared plus n into n minus 1 into n minus 2 upon 3 factorial, that is 6 into negative r cubed and so on. So if we do this, we will find that this expansion is literally 1 plus r squared plus r cubed plus so on. And what is that? That is nothing but GP, a plus ar squared plus ar cubed. Right? You can check it by yourself, okay? So, sum of terms of a geometric progression whose common ratio has absolute value less than 1, it actually works. Okay, you can use this binomial theorem to arrive at that result, or you can also use the standard result from geometric progression to arrive at the same result. But the reason why I opened this topic right now is different. Okay, it's good to know this. You will definitely study this in your next year. Okay, and this topic is called validity of expansion. Okay, validity of expansion of binomial. Okay, take the instance of this. Okay, suppose I say that 1 upon 1 minus x is 1 plus x squared plus x cubed plus x raised to 4 and so on. Okay, what have I got this from? Where I have got this from? We have got this result from binomial theorem, correct? We have got this result from binomial theorem, and binomial theorem has given us that result, and that's this. Okay, what I have done is I have just taken a as 1 and I have replaced r by x. Okay, I have replaced r by x. Now tell me, if I take x as 2, clearly RHS is going to be infinity. But what about LHS? LHS will be negative 1. So is the expansion valid? It's not valid. Which means, although in many textbooks they mention the formula correct, okay, and we often tend to learn the formula and remember it, what we do not remember is this particular equation. On one side we have a term, a rational function, and on the other side we have an infinite series. This is valid only when x belongs to open interval minus 1 and 1. That's important. Now you might say that 1 does not belong to the domain of this function. Agreed, 1 never belongs to the domain of this function. But in addition to that 1, there are other numbers also for which 1 upon 1 minus x is defined, but it gives a finite value, but the other thing on the right side doesn't give a finite value, it gives us an infinite value. Okay, so by validity I mean you have to pay attention to where are we using that formula. Okay, where are we using that particular binomial expansion? Is it valid or is it invalid? Because if it is invalid, then we cannot use it in our analysis, no matter in what topic of physics or any other topic of mathematics we are discussing. Do you follow this? Validity of expansion is important. It's almost like specifying domain of the function. Like say tan x. We blindly say derivative of tan x is x squared x. We might be aware of the fact that tan x is not defined for all real numbers. Whenever it is defined, its derivative is x squared x. Same thing here. When we are using the binomial expansion, we should ensure that the value of x for which we are doing it, it is in that particular range, -1 to +1. Now we know this from geometric progression perspective because we have obtained that result in the context of geometric progression. But the same things should be also applied to other expansions of binomial theorem where n is not a natural number. Okay, there is a different topic related to this to check or to find the regions of validity or intervals of validity. We'll study this later, but they might set a question on this. Okay, something which will require you to use that 1 upon 1 minus x's expansion is valid only when x lies between -1 and +5. Okay, so keep that in mind whenever binomial theorem is being used. Okay, fine. So that's it with the theory.